Okay, great. I like recording these for you guys because I think you can come back later and watch them again. If you subscribe to the channel, sometimes if you just hit subscribe, it'll come up. This lecture today is going to be from chapter 17 of the textbook. It's a really good textbook. You all did delve into it, I think, at least a little bit, or most of you did. You answered the questions for the homework. And you start to see what's in there. Hey, there's some really good information. Now, chapter 17 is assigned to read. This is required reading. Read chapter 17. Okay. What I tell you in class is going to be great and helpful, but this will give you more information, more examples. And if you really want to test your knowledge, go all the way through to the end of the chapter and start reading some of the questions yourself and see if you feel like you could answer these questions. They might also show up on the tests later. So this chapter is about making inferences from a population mean. Now, this book jumps around a lot or maybe I jump around a lot. We go in a different order. They start with regression. I start with t-tests because to me, that's a simpler test. It's simpler mathematically. To me, it's simpler conceptually. Different opinions about that. Actually, they even start with a z-test. I skip the z-test. I'm only going to talk about it for a moment because it's not a test that we really use. It's really just a teaching tool. The t-test is a test that we use a lot. But to understand what a t-test is, we also have to go over some other really basic concepts, like what is a hypothesis test? What are the assumptions that we have to meet? What's a p-value, right? So we'll go over that today. And we're going to use some other resources. So you won't just have to listen to me talk. You'll also get to listen to other people talk because there are some really good YouTube videos on this. And while I would like to believe that my YouTube videos are awesome, there are people who have teams. They have a cameraman and a script and setting and a graphics team, and they really pull it together in a really nice way. So I'm going to share some of those with you today. So this lecture, again, is called Introduction to Hypothesis Testing, Comparing Means with Confidence Intervals and a One-Sample T-Test. Again, read Baldi and Moore, chapter 17. This is required. So why test hypotheses? Why test hypotheses? We test hypotheses to use our sample data to make inferences about a larger population. Remember, we talked about populations and taking samples from them. And so this allows us to answer questions about differences or about relationships. So for example, we might want to know, is the average height of people in our class different from the national average? Hint, hint, that's lab on Thursday. And for that, we would do a one-sample t-test. Or we might want to know, are freshmen taller on average than sophomores? Maybe the younger generation is getting taller. That would be a two-sample t-test because now we have two samples, two means. Or we might want to know, do students in different majors differ in height? That would be an ANOVA because now we have several different groups. I think our class has 4 majors. Is there a relationship between student age and test scores? Do older students do better on tests? Do younger students do better on tests? Here, actually, we wouldn't be comparing means. What we'd be comparing is a continuous distribution and the relationship between age and scores. And for that, we would use a simple linear regression. We'll get into all those tests later, but for now, I want to introduce some of the concepts of hypothesis testing using the one-sample t-test as an example. Hypothesis testing steps. We will use these steps over and over and over in class, okay? Introducing them now, but we'll use them again and again. This would be a good time to get out your pen and your paper and jot some things down. I know you can see it on the PowerPoint. I know you can take a picture of it on the PowerPoint. I know you can go back and read it on the PowerPoint later or watch the video later, but if you write it down, it will help you to remember. Step 1, specify a null and alternative hypothesis. For example, our null hypothesis, often written here as H sub O, is that there is no difference in mean test scores for students who attend class versus those that do not attend class. No difference in scores for students who attend class versus those that do not attend class. Null hypothesis means nothing going on here, right? The alternative hypothesis, often referred to as H sub A, is that there is a difference in mean test scores for students who attend class versus those that do not attend class. I don't have those data, but I wonder which way it would go. The next step is to select your significance level, your alpha. We call it an alpha, and we use the Greek letter alpha for your p-value. It is customary in biology to use an alpha of 0.05. That's our cutoff value. Now, this cutoff value is essentially arbitrary and can vary from field to field. It can also vary based on the kind of data you're collecting or on the number of tests that you do. We will use a p-value of 0.05, an alpha value of 0.05, because it's customary, but just understand that it's an arbitrary number that was set by tradition by Fisher, I think 100 years ago, but we still use it. And you'll see a little bit later why it kind of does make sense. Step 3, collect data. This is the fun part. Measure stuff, right? Go out and measure stuff in the world or collect data from the internet, something. In our class, we're going to collect data about ourselves, and we'll take data from the internet as well. And then run the tests. So you have to decide what test is right for your data, and then we're going to use R to run the tests. And then the final step, step 5, is to interpret the results and draw your conclusions. So how do you answer the question? Do you accept or reject the null hypothesis? What evidence do you have to support your conclusion? The means, the difference in the means, test statistics, p-values, and we'll explain more about what these are today. And then you explain what your conclusions mean in light of your background research, right? Let's say you did some research and you found somebody else's study that said students that attend class get higher test scores. And you thought, I wonder if that's true for my class. So you took a sample of students from your class, you recorded their attendance, and you recorded their test scores. They decided to share that with you, even though it's private information. Maybe they did it anonymously. And then you ran a t-test. This would be a two-sided t-test. Students that attended and students that didn't. You set an alpha of 0.05, and you ran the test, and you found out, yeah, actually, the students that attended class had a higher mean test score, and your p-value was less than 0.05, so it was significant. So you reject the null hypothesis, and then you say, well, what does this mean, right? Okay, yeah, but why? And you might think, well, maybe because when students attend class, it shows that they're more engaged. Or maybe it's because the information they get while they're in class helps them to learn it. Or it could be that going to class helps them to meet other students and then they study together. Could be a lot of reasons why, but you interpret it. Or you can just say, well, hey, it doesn't even matter all that why. Attend class and you'll do better on the test, right? So what is a p-value? I've started talking about p-values, but now we need to explain what it is. A p-value, and how will it help me pass statistics? A p-value is something that's a little bit hard to wrap your head around, but don't worry about it too much. Just understand that P stands for probability, and you can think of it as the probability of obtaining results that are at least as extreme as the observed results if the null hypothesis is correct, right? So that determines the statistical significance. And just remember that if P is less than 0.05, you reject the null hypothesis, your H sub 0. In other words, you can accept the alternative hypothesis. And that means that the probability of getting the sample data that you got, if the null hypothesis were true, is less than 0.05. That's pretty uncommon. That's pretty uncommon. Again, it's arbitrary. You could set it at 0.01 or 0.1, depending on how you think it should go. But if you set your alpha at 0.05 and your p is less than 0.05, you reject the null hypothesis. You say there's nothing going on. There is something going on. There is a difference between the means, or there is a significant relationship depending on the test you're doing. Now, if the p is greater than your alpha, greater than 0.05, you fail to reject the null hypothesis, right? You don't say nix-nay on the HO. You say, maybe we have to accept the null hypothesis. There is nothing going on. The probability of getting these data are actually pretty high, a pretty high random chance that we would just get these data even if there's nothing happening. So now I'm going to show a video, or at least I'm going to start watching this video with you from Crash Course Statistics. And I want to show you about this series of videos too, because it's a very good series of videos.
So we aren't able to hear what she's saying.
Oh, you can't hear? Okay, that's fine. You know what? I will just say this video exists and you have the link and you should watch it. You can watch it on your own. It's 10 minutes and it'll help you a lot to understand hypothesis testing and p-values. All right, it's really well done. Okay, why alpha 0.05? Why alpha 0.05? Well, it's historical, it's traditional, it's just commonly used, it's well accepted, but it's also that it means that, let's say you had a population, right? You have a population and you take a sample from that population and you take another sample and another sample and another sample. And each time you take a sample, you calculate the mean of that sample. Let's say you had a population of students and you take a random sample of 30 students and you calculate the average height. And you take another sample of those of 30 students and you calculate the average height of them. And you keep doing that over time. Sometimes, just by chance, your average will be way over here in the tails. You'll get an average that's really small. And sometimes you'll get an average that's really big. But most of the time, you're going to get an average that falls within that central core of the distribution. So it makes sense. It's sort of it's just a cutoff value that we use. Sample means are rarely going to be in the tails, right? We'll get them less than 5% of the time. So the probability of getting a data point that extreme or greater would be pretty small. Why not more small or bigger? Why not 0.1, like 10% of the time? Why not 0.01% of the time? Again, it depends on your field, it depends on your data, but this is what we normally use. So the t-test was created by someone named William Gossett over 100 years ago. And he was a Guinness brewer in search of quality control for beer. And since you can't hear the video, I have a link for it here, but watch this video. It's a really good video. It talks about the relationship between statistics and beer. And I don't know, who here likes beer? Raise your hand if you like beer, or if you've ever maybe liked. I used to like beer. I don't drink it much now, but beer is great. So this man worked for the Guinness Brewing Company, and he developed a system for determining how sample means relate to population means, and developed a test called the t-test. So the one sample t-test is used to compare your sample mean to a hypothesized mean. There are different forms of t-tests. The t-test that we're going to learn about this week is the one sample t-test. There's also a two sample t-test and a two sample paired t-test, but we're just going to talk about the one sample. And this means we're going to take a sample mean and compare it to a hypothesized mean. The example we're going to use is to take a sample of student heights, us, our class, our student heights, and we're going to calculate the mean and the standard deviation. And we're going to compare that to the national average of adult heights, right? And we're going to compare that hypothesized mean with our sample mean. And we're going to see if we're different from the national average. And we may be not. I don't know yet. We won't find out until we collect the data and we run the test. So we're doing real research in this class almost every week, finding out new information. I have the code written out, but I don't know the answers. We're finding them out together. The T statistic is a statistic that we calculate that says where your data are located in the T distribution. Okay, so the T value, also known as the T statistic, basically will show up over in one end of the distribution or the other end of the distribution if the p-values are small. If the test statistic is larger than the T critical value, then P, the probability of getting those data by chance if the HO were true, is less than 0.05. And you reject the null hypothesis and accept the alternative hypothesis. So now there are two ways of doing this. There are two ways of doing this one sample t-test. One way is to have a one-sided t-test. A one-sided t-test asks the question, is my sample mean larger than the population mean? Or is my sample mean smaller than the sample mean? It's like you kind of guess which direction it would be. For instance, in Hawaii, we might expect that we're shorter than the national average because we tend to be shorter here than people in other places. We might say, is it true? And so it depends on what question you're asking. Are we shorter than the national average? But maybe you don't really know which way it's going to go. It could be shorter, could be taller. So then the question you're asking is, are we different? Are we different than the national average? And that would be a two-sided t-test. Okay, so one-sided, you have a hypothesis about which direction it's going to go, larger or smaller. Two-sided, you split the tails each way. And the t statistic is simply calculated as t is equal to x bar, which is our sample mean, minus the population mean, divided by the standard deviation, divided by the square root of n. And you probably already remember this standard deviation divided by the square root of n. That's our standard error that we calculated last week, right? Okay, every statistical test comes with a set of assumptions that must be met for the test to be valid. In this case, here I've listed 4 assumptions. Some people put this as 3, some people put it as 2, depending on how you group them. I put that the first assumption that must be met is that the samples, the observations, are independent and random. That is, when you draw a sample, when you draw an observation from your sample, drawing that observation, measuring that person doesn't change the measurement of the next person. They're independent. If for some reason you measuring something affects the next measurement, then they're not independent. They're somehow connected. They're related. They would not be independent anymore. And that happens in the paired t-test. But in this case, you want those samples, the observations, to be independent. Also, they have to be random. If there's some bias in the sample, then you can't really compare the populations. If you said, well, I want to compare these samples, but I'm only going to measure people that I think are already short, and that way I'm going to prove to myself that my hypothesis is right and that people in Hawaii are shorter. That wouldn't work, right? That's biasing your sample. So you have to have a random sample that includes a potential for every individual in the population of interest to be sampled. Now, if we're saying that UH Hilo students are shorter or different than the national average, we would need to get a random sample of everybody at UH Hilo, but we're not doing that. Our sample is kind of biased in some way because it's just the biostat students. Is there any reason to think that the biostat students would be systematically different from students in the general UH Hilo population? I can't think of any reason why. I actually think that our sample is pretty much random. I don't think that people self-select to go into biostats if they happen to be taller or they happen to be shorter. So I think that our class sample is probably a pretty random, unbiased sample. And I see no reason to think why measuring one student would affect the height of another student. So we got that, check.
It looks like we have
Numeric
a question.
data. Yeah,
So
What was in that formula, the lowercase n's for,
in the last slide.
yes,
And the last slide, the lowercase n here is sample size.
oh,
Sample size, the number of observations in the sample. That's like what we did last week in the spreadsheet. The second assumption is that you have to have numeric data. This doesn't work if you're measuring nominal data. It can't be like, you can't take an average of colors. Unless you converted it to a numeric number like RGB, something like that. But otherwise, it's got to be numeric data. And you got to watch out for ordinal data or categorical data that also looks like numeric data. It could be the number of stars, with 1 being poor, 2 being good, 3 being, much better, right? The number of stars looks like numeric data, but it's actually a categorical variable. Watch out for those. That's not numeric data. But height, student height, that's a numeric data. It has to also come from a normally distributed population. That can be a little bit of a tricky one, and we will investigate some methods for how to tell whether or not this assumption is met. The fourth assumption is equal variances, and some people leave this one out because you can also do a Welch's test. I think by default R does the Welch's test, which does not assume equal variances, and that's pretty easy to do. So this one's kind of like, yeah, you may or may not need equal variances among the samples. So for the t-test calculation, to calculate the test statistic, which I kind of showed you before, but now we'll go over it in a little more detail. You need 4 things. 4 things. That's it. You got these 4 things. You can actually do this by hand. It's a pretty simple calculation. You need the mean of your sample. You need some hypothesized mean to compare your sample mean to. You need the standard deviation of your sample, which we now know how to do. We could do that by hand too, right? And you need the sample size. How many observations did you take? Right? Easy. And then you just plug it into this formula. T, your T statistic, your test statistic, is equal to the mean, the sample mean, minus the population mean. So the difference between those two means, divided by the standard deviation, divided by the square root of the number of observations. Simple, right? So here's an example of a one sample t-test. This is from the book. Baldi chapter 17, example point 3. This is body temperature. So a publication in 1868 established 98.6 degrees Fahrenheit as the mean body temperature. You probably all heard this. 98.6 is our body temperature. If you have a fever, you're higher than that, right? Now, a simple random sample, sometimes you'll see this SRS, simple random sample, of 130 healthy adults were measured, and they got a mean of 98.25 with a standard deviation of 0.733 degrees. That's a little different. Is that statistically significantly different? Is that really different, in other words? Or could you have gotten that just by chance? This random sample of 130 adults is just a little bit different, but it's within a range that we would accept as being close enough, right? So what you can do is a one sample t-test, and here's what the results might look like. So a test of mu, which is your population mean, is equal to 98.6. Sorry. test of mu, in this case, it should be population mean, but this is saying our sample mean is equal to 98.6 versus 98.6. Okay, N, see here, N, 130. How many healthy adults did we measure? Up here it says 130. 130 observation. Our mean, 98.25. That's what it says up here. We got a mean of 98.25. Our standard deviation, 0.733. That's what we also found right here. We just plugged it into the computer. The standard error of the mean, which is the standard deviation divided by the square root of n, is 0.0643. And the 95% upper bound of the confidence interval. We haven't talked much yet about confidence intervals, but we will more. It's another way of describing the variation of the data. The 95% upper bound would be 98.35. Right? 98.25 is the mean, and the upper bound of the confidence interval is 98.35, so plus 0.1. And the t value, the test statistic for this test is a t, is negative 5.44. So whether the t value is negative or positive, if it's a large value, a large absolute value, that means that the p value will be small. And in this case, the p-value is very small. It says here that the p-value is 0, straight up 0. That's not right. It's not 0. It's never exactly 0. It's just less than 0.0001, right? It's just less than that. So that's how you would read the results. And this means that who thinks that this means that we reject the null hypothesis? Raise your hand if you think we reject the null hypothesis. Give me a hand. Give me a hand. You guys get this little tool where you throw hands up, right? I'm not seeing them. How many people think we reject the null hypothesis? Yeah. We reject the null hypothesis. The p-value is less than 0.05. It's 0.000000 something. It's less than 0.05. So we reject the null hypothesis. There is a difference. This group of 130 healthy adults has a body temperature that is significantly different than the established mean of 98.6. I wonder why. I wonder why. Has human body temperature changed over time? Was that established mean not a very accurate mean to begin with? I'd like to look into that more. I've read something about this, and I'm actually curious to know. Okay, so where do we get these p values, these magical p values? Where do these come from? Okay, there is a place in your book at the end of the textbook that has a lookup table that looks like this. And every stats book, I think, has it. I had to look today. I'm like, do they still put those in there? They do. At least they did for this one. And so this lookup table is what we actually used to use to find the t critical value, the t critical value. So for this to work, what you need to know is here, if you look over here on the left side of the table, it says degrees of freedom. Remember, degrees of freedom for the t-test is n-1, so number of observations -1. And we had 130 adults, right? So it would be 129 is our degrees of freedom. So you'd go down here. Well, 129 is somewhere between 100 and 1,000. So you'd go down here. And then on the top, you decide your confidence level. So if our alpha is 0.05, you just say 1 minus 0.05 is 0.95. Convert that to a percent. Confidence intervals are usually converted to percentages. You say 95%. So at an alpha 0.05, that means a 95% confidence interval. So you decide your confidence interval, you see 95 right here. So you go down this column, whoops, you go down this column and across this row, and you see that your, oh, this is for a z-test, actually. This is the wrong, not the t-test. It's pretty similar. But you would combine, you'd find these and you say, okay, this is my critical t value. If my t value is greater than this critical number, then my p-value is less than 0.05. You wouldn't have an exact p-value, but you would know that it meets that cutoff, and you would reject the null hypothesis. Confidence intervals. So let's talk a little bit about what we mean by confidence intervals. Again, this lecture, we've got a lot of new concepts. You're going to have to remember these because they will come up again and again and again. But we'll keep practicing them. So what's a confidence interval? What's a confidence interval? A confidence interval is simply a range of values around a sample mean that contains the true population mean to a specified probability or confidence level. You might think of the margin of error. You've probably heard of the margin of error. So the margin of error for a t-test would be calculated as that t-stat, right? The t-stat, the t-critical stat you got from the lookup table or that you got from your analysis output, multiplied by, the asterisk is multiplied by, your standard deviation divided by the square root of n. And this, remember, this is the standard deviation divided by the square root of n is your standard error. So t times standard error is your margin of error, right? That's your plus or minus 95% confidence interval. So you would say your confidence interval is your mean plus or minus t times standard error. And here's another video, 3 videos, 3 videos. Here's another one about understanding confidence intervals. Please watch this. Watch all these videos. This one's 5 or 6 minutes, really short. It'll help you a lot. A little bit more about confidence intervals. This helps to visualize it. So the 95% confidence interval contains most of the data, right? 95% of the time, it contains the true mean. Less than 5% of the time, the true mean will fall out of that. It can happen. If you took 100 samples from a population, 5 of them will fall outside of that 95% confidence interval, but you're willing to take that risk because 95 of them will be in, and that's good enough. The best we usually want to do. So here's another example of calculating confidence intervals. So data on the blood cholesterol levels of 24 lab rats were collected, and we got a sample mean of 85 and a standard deviation of 12. Remember, all we need is the mean, the standard deviation, and the sample size, right? And now we just want to calculate the confidence interval, the 95% confidence interval. So this is a little excerpt here from the lookup table. This is confidence level C. We had 24 lab rats. 24 minus 1 is 23. So our degrees of freedom here is 23. And then we say we want a 95% confidence interval. So we go over here and we can see our 95% confidence interval T, critical T stat, would be 2.069. So we could calculate our margin of error, again, is T times standard deviation divided by the square root of n, or 2.069 times 12, which is the standard deviation, right, up here, divided by the square root of n, remember, 24 here. Do the math, it's 5.07. So we could say the mean is 85 plus or minus 5.07. The mean is 85 plus or minus 5.07, 95% confidence interval. 95% of the time, the mean is within 5.07 of 85. So most of the time, it's somewhere between 80 and 90. The assumption of normality. So moving on to how to check the assumption of normality. This can be kind of tricky. And I was reading about this a little bit more because I was trying to think about, there's different ways that people do this. And there is some debate in the stats community over the right way to do it. Not everybody entirely agrees. But generally, we start by making a histogram. We make a histogram, and that helps us to see the shape of the distribution. Last week, we looked at a ton of histograms, right? Because I wanted you to get an idea of what these histograms tend to look like for normal distributions and for other kinds of distributions. So you start by making the histogram, and you can start to see, oh, does my distribution look pretty normal? You could also make the box plot. That can help to see. Although, again, it can hide bimodal data and can't always see what's going on there. There's also the QQ plots that we talked about and we looked at, where you calculate the z-score and you plot that against the rank of your data. And you plot the z-score and you plot that against the actual data. And then there's a normality test. So this is another hypothesis test that you do before you do the other hypothesis test to test your means. The hypothesis test for the hypothesis test. It's like cheese food. It's not cheese, it's what you feed your cheese. Anyway, so the normality test, there's lots of different kinds of normality tests. In Minitab, we use the Anderson-Darling test. In R, the default is the Shapiro-Wilks test. That's what we'll use on Thursday. The null hypothesis for the normality test is that the data are normal. The data distribution is normal. The alternative is that the data is not normal. So here's a situation where you're actually hoping that your p-value is greater than 0.05. You don't want to reject the null hypothesis. You want normal data because that just makes it easier. You can use the parametric statistics, right? Right. Here's some caveats. The T procedures that we will use are exactly correct when the population is exactly normal, which is very rare. It's very rare. Real populations in nature are just a little different than that. But lucky for us, the T procedures are robust to small deviations from normality. The sample still must be a random sample from the population, and the outliers or skewness will strongly influence the mean and therefore affect the validity of the t-test. But as the sample size gets larger, that influence becomes less important because of the central limit theorem, which I'll get to in 2 more slides. So rules of thumb for the sample size, right? How big is a big sample size? How big is big enough? When n is less than 15, the data must be close to normal without outliers. That's a small sample size. When you have 15 to 40 observation, you've measured 15 to 40 students, some skewness is acceptable, but no extreme outliers. That's going to mess up the data. When your number of observations is greater than 40, some people say 30. Of course, these are rules of thumb. Stats people probably will argue about this. The test statistic will usually be valid, even with strong skewness. All right, so the t-test is robust to some violation of the assumptions of normality. So what do you do if your data are really, really not normal? Well, one thing you can do is try transforming the data. Here's a classic example from your textbook. And this is a graph here on the left of body weight in kilograms against brain weight in grams. And if you put lots of different species on this graph, you've got dolphins and humans and hippos and elephants, you can see there's such a huge range in body weight. This these data do not come out being normally distributed. This is on a scatter plot. You can see it. If you made a histogram, you would also see that. But if you take the log of body weight and brain weight, you get a very nicely distributed sample. And this would come out as normal, and it works better for the t-test. So that's one possibility. We'll talk about that more in class. We'll talk about more transformations. There are lots of transformations that you can do. Another option is to use a non-parametric procedure like the Wilcoxon-Rank sign test. There's lots of different non-parametric procedures. The non-parametric procedures that we'll talk about in class are some traditional ones. We probably won't have much time to get into some of the more modern ones, but just know that they exist and that there are lots of different ways of analyzing your data besides the parametric test that we'll mostly use in this class. And here's a table that shows you, I love this table. I just found this today. I was, oh, this is great. It shows you the different data types and the different tests. Now, if you have this table, you can pretty much figure out what test to use. So remember we talked about data types, I think the first day or day 2. Now for a t-test, we need what kind of data? We need quantitative data. We need quantitative data. So if we have quantitative data and it's non-normal, it's discrete or it's non-normal, we can use the Mann-Whitney test or a log rank test. If it's quantitative and it's normal, we can use the student's t-test, right? This is what this section is. This is the part we're talking about this week. We will eventually get into all of these other tests, and this table will come in handy. You will eventually want to memorize this table. More about the central limit theorem. The central limit theorem. The central limit theorem is a little bit confusing. It's like, what are they trying to say here? I break it down like this. This is the most helpful way for me to think of it. The distribution of sample means approaches normal as sample size increases. So if you took, if you have a population and the actual population is not normal, it's exponential, but you took a bunch of individual observations from that sample and you plotted them on a graph, they would come out looking like this. They would come out looking not at all normal. They would come out looking exponential. But if you took a bunch of samples of 2 observations and you took the mean of those 2 observations, right? You took 2, took the mean, plotted that. You took 2, took the mean, plotted that. Took 2, took the mean, plotted that. It starts to look a little bit more normal. And now if you took a bunch of samples with 10 observations each, take a sample of 10, take the mean of those 10 and plot that on the graph. Take another sample of 10 individuals. Take the mean of that. Plot that mean on the graph. And another one, and another one, and another one. And each time you draw a sample, you draw 10 and you plot the mean on the graph. Your distribution starts to look pretty darn normal. Now, if you go up to 25 individuals per sample, 25 observations per sample, and you plot those means, your mean is now pretty darn normal. And this is something that really helps us out a lot, because if we have a big enough sample size, we can invoke, in a sense, or rely on, or just know that it's going to work out because of the central limit theorem, that means do tend to approximate a normal distribution, even when drawn from a non-normal distribution. And I say that here from the textbook. I've quoted the textbook. You can read this yourself. It gives you all the detail, but it's basically just what I said. Okay, z-test. The z-test, I'm just going to bring this up briefly. We will probably not need to use it because the z-test is something that you only use when you know the population standard deviation. And in actual practice, we very rarely know the population standard deviation because we don't measure the whole population. I use this example of a rare test for a rare bird. I think about the alala. I've brought them up before. I'm very fond of the alala. They're a very rare species of Hawaiian bird, the Hawaiian crow. They're all in captivity. So if you wanted to measure the weight of alala, you could theoretically measure all of them, the whole population, put them on a scale, get the weights, and then you would have the true population mean and the true population standard deviation. And then you could use a Z test to compare that to another value, for example, another population of birds or something. But in actual practice, we mostly have to take samples and then we make inferences about those samples to the larger population. And for that, again, we use confidence intervals and t-tests. So here's kind of a lot of words to sum up everything I just said. There's a lot of words to sum up everything I just said.
And we have
I
a
put the-
question.
Yeah.
She see us on this.
Yeah,
Oh. Eamon, you talk about the alala, it is, or alala is all in captivity on the island.
Yeah, they're all in captivity. I think some of them are not on the island, but yeah, there's 100 and
Right.
as of the making of this slide, this is the data I had. It might have changed since then.
Right, we would call this like biased data right off the bat, because we're dealing with weight and we would change with wild habitat versus. Do you think so?
Well, but that's not what we mean by bias in statistics. In statistics, what we would mean by bias is a sample that does not represent the population. So like, let's say you wanted to know the weight of all the alala, but you're not going to measure all the population. You only have enough time or money or bandwidth to measure 20 of them. And the 20 of them you have are all at, I think there are some, I'm going to kind of make this up, but let's say that they're all at the San Diego Zoo. So you're at the San Diego Zoo and you measure all the alala there. You measure the weights and you say, okay, I'm going to take the mean, I'm going to calculate my confidence intervals, and I'm going to say my population, I'm going to make inferences about the whole population from this sample that I measure at the zoo, at the San Diego Zoo. But maybe at the San Diego Zoo, the founder population came from a source that was genetically different than the rest of the population. Let's say they were all just a little bigger. They were a little bigger, or maybe because after years of being in captivity in a temperate area, they just got bigger, they were better fed, something like that. For some reason, that sample, that part of the larger population is inherently different. It is no longer representative of the whole population. That would be a biased sample. But if you're measuring the entire population, you can't have bias because you're measuring all of them. Does that make sense?
Yeah.
Okay. Again, I put all these slides here with lots and lots of words for you to read and as a study guide, summing up what we just said about hypothesis tests as a way to assess the evidence provided by the data regarding some claim or hypothesis about the population. More specifically, they are a way of comparing observed data with a hypothesis about some characteristic of the greater population. The hypothesis is a statement about some parameter of the population, usually expressed as null and alternative hypotheses. So the null hypothesis is a statement of no effect or no difference in the parameter being measured compared to a hypothesized value of the parameter for the one sample t-test. It's abbreviated as HO. learn it now, you'll see it again and again. The alternative hypothesis, or HA, states that there is a difference between the parameter being measured and a hypothesized value of that parameter. The result of the significance test of the hypotheses are expressed in terms of a probability, or p-value, that measures how well the data and the hypothesis agree. Confidence intervals are appropriate when our goal is to estimate or make inferences about a population parameter, typically the mean. So at what point do we have enough evidence to reject the null hypothesis of no difference and accept an alternative? It is generally accepted that if a result or difference can occur by chance less than 5% of the time, assuming the null is true, then we should reject the null and accept the alternative. An alpha level is the predetermined probability at which we decide to accept or reject the null, and is often set to 0.05. Test statistics like the z-value and the t-value, and later when we do an ANOVA, there'll be an f-value. These are what we calculate to determine how far our sample data diverge from the hypothesized value, or null hypothesis. P-values can then be determined from the test statistic to compare with the alpha value to tell us whether we should accept or reject the null. And that is the whole lecture. Wow, we got through it. Oh, I think I have a couple other things on here I just wanted to give you. This is just, again, for you as a study guide. The stat symbols, we went over these before, but just to throw them out there again. N means sample size, M, capital M, is median, mu is the population mean, X bar is the sample mean, sigma is the population standard deviation, although often people use sigma when they're talking about the sample standard deviation. And S is the symbol for the sample standard deviation. You'll see these symbols again and again. So here's a little list for you. And just to remind you, this is what we did last week, standard deviation and standard error. So for a sample size of n, the standard deviation is the square root of 1 divided by n minus 1 times the sum of the differences squared between the mean and each sample observation. And the standard error is the standard deviation divided by the square root of n. I won't expect you to memorize this big formula. This big formula for the standard deviation, you don't have to memorize it. But you do have to know this, the formula for standard error. It's pretty simple. I think you can learn it. And it's also something that you will see a lot. Scientists often present their sample results as the mean plus or minus the standard error. Sometimes plus or minus the confidence interval. Sometimes standard error. When you're presenting your results, always specify. That way we can be sure and we can know.
Can you go back to that symbol?
The last slide?
Yeah.
Yeah, why not? Sample standard deviation.
The slide.
Oh, this is the slide before.
Oh, the slide before, the stat symbols.
And do you think it would be useful to show them the explain to a 10-year-old? Potentially?
The explain to a 10-year-old for, yeah. Let's try explain to a 10-year-old. What does anyone have more questions about? P-values, hypothesis testing?
Which term confused you guys the most? Was there one conceptually? Yeah.
Let's try explain p-values
Mhm.
to a 10-year-old. All right, imagine you have a magic coin and you want to know if it's a fair coin that has an equal chance of landing on heads or tails. To test it, you flip the coin 10 times and get 7 heads and 3 tails. Now, the p-value is like a measure that helps you decide if your coin is fair or not. If the coin is fair, you would expect it to land on heads about half the time. But if you just got lucky and it landed on heads 7 out of 10 times, it doesn't necessarily mean the coin is unfair. The p-value is like a way of asking, if the coin is really fair, how likely is it to get 7 heads out of 10 flips just by random chance? If that likelihood is very low, you might start to think that maybe the coin isn't fair and something else is going on. So in simple terms, the p-value helps you figure out if the results you got are just a fluke or if there's something interesting happening. If the p-value is very small, you might question the fairness of your magic coin. If it's large, you might think, well, it could just be luck, and my coin might be fair after all. Does that help?
Yeah, so I've found that using Chat GPT to help try to simplify these concepts that for me are sometimes hard to grasp. Because sometimes I'll look at the definition of a p-value, and I'm like, for me, that doesn't click. And I'll look at other resources, and they're made by the same genius people, and they also, it's still also in terms that don't quite click. So using this tool to try to, I don't want to say dumb it down, but simplify it into terms that might help your brain click is very useful. And it helps translate it. So if anyone has any troubles with these things, possibly try this, and you can use it for any term or any concept really. Because whatever makes it click and helps you understand is useful.
Mm-hmm. Yeah, I just looked up how to explain confidence intervals. Now, I also have the video on it. I think the video is really helpful because it has nice graphics that help to visualize it. I think human beings are more visual, but let's see what Chat GPT comes up with. All right, let's imagine you have a friend who's really good at guessing the number of jelly beans in a jar. I've actually tried using statistics to get the jelly beans in a jar. I was like, I want to win. I can get this. I'm going to take a sample. Okay, I'm going to take a few samples and I'm going to weigh the, and I got the standard deviation anyway. All right, let's imagine you have a friend who is really good at guessing the number of jelly beans in a jar. Now, your friend doesn't always guess the exact number, but they're usually pretty close. Confidence intervals are a way to show how sure your friend is about their guess. So let's say your friend looks at a jar and says, I think there are about 100 jelly beans in there, but I'm not exactly sure. It could be more or a bit less. The around 100 part is like the guess, and the a bit more or a bit less is the confidence interval. It's the plus or minus, right? A confidence interval is like a range of numbers that your friend is pretty confident the actual number lies within. They might say, I'm 95% confident that the number of jelly beans is somewhere between 90 and 110. The confidence interval helps your friend express how certain they are about their guess. If they say 99% confident, then the range might be wider, like 85 to 115. because they want to be more sure that the actual number is in that range. So in simple terms, a confidence interval is like a way of saying, I think the answer is around this number, and I'm pretty sure it's somewhere in this range. It helps your friend show how confident they are in their guess without claiming to know the exact number. So yeah, if you said I'm 95% confident that the number of jelly beans is somewhere between 90 and 100, then you could say the number of jelly beans is 100 plus or minus 10, right? That's how you would express it. Plus or minus 10, 95% confidence interval. Any questions? Okay, great. So again, please pay attention to the emails. I'll be sending out the R code for the lab on Thursday. Do your best to install ggplot2, make sure it's working. If it's not, please come to us ahead of time so that we can help you. And thank you very much.
Thank you.
Thank you. Watch the videos. Watch the videos on your own. They're short and fun.